Okay, bom dia, good morning. So let's continue looking at boundary value problems numerically, and we saw a little bit of an easy version of a shooting method. So now we have, so we're looking at the shooting method. Our ODE is this one, no, nonlinear one. Okay, and so what we want to do, inspired by last time, we want to construct a family of initial value problems. Last time we saw a linear case where there was a trick using superposition that we could solve two linear initial value problems, put them together, and we were solving actually the boundary value problem. Nice trick to know. And anyway, we still would have to solve those two initial value problems. I also mentioned, and you know, I'm not going to get into details of shooting method. I mentioned you there's actually a book I mentioned last time by Herb Keller, which I think is a science book now. Already, you know, has from the 60s or 70s, specialized in shooting methods, and you know, one could analyze cases where there's instabilities, this and that. I'm not going to get into the details. I just want to show you this possibility. In particular, the course is more on PDEs and ODEs. And but I also mentioned, I'm not showing, right? And this, I think, you would see, for example, in the more elementary book by Burden and Ferris, that you also can solve this boundary value problem just by putting a different scheme in space. If we think of this in space, sometimes I think I mentioned this as time, but we can think of it in space, right? Now I'm going to get a parameter which is t, which is not time, but anyway. But not to get confused, because sometimes we transform the boundary value problem into an initial value problem. Then when we transform it, the initial value problem, we can think as time in sort of an orbit trying to hit a target, right? Many different ways of interpreting. And one way, which I'm not showing here, which is kind of trivial for you, for sure, is also just doing a finite difference scheme and then having a system, right? And solving the system. So usually the method we saw last time is faster, the shooting method, in the system, because you have to solve a system. But sometimes it can have instabilities and so on. So I just wanted to mention this. Okay, so having the system is also is easy to do. Okay, now let's see this. This is kind of a fun thing to do also. Sometimes we might have problems. We're not going to analyze it. But how can I transform this problem now into an initial value problem? That's the shooting method, right? And as the name says, you try to shoot and hit the target. Okay, we saw how to do this last time by superposition. Now it's really going to be more like a shooting method. I'm going to try to hit the target once. I missed it. I'm going to try to hit it second time. I miss it. I'm going to try to hit the third time. The things that we hope to improve at each step, right? It's not just random shooting. And this is then how we'll see how, at least how the strategy for this guy is built, okay, without getting into details of numerics and stability and this and that. And we'll see exactly something that's going to come up that we know that sometimes is unstable. So let's see. So let's see how this comes. Okay? So what we want to do then is to rewrite this problem like this. Okay, this is just a parameter. Okay, and basically the name probably comes from this, right? This is A, this is B, this is X. This is alpha. Yeah, this is alpha. This is beta. This is our target. And this is our angle at which we're shooting, right? And we hope then to learn, right, from missing the target. So what we want is we want to construct a sequence okay, so that, let me actually put the index right. So that in some sense, okay, we're not going to prove this, but we would like to know, or at least in the informal way, to get a feeling that this here will happen. Right, that we eventually will hit the target. Okay, so how can we build, at least in an intuitive way, because we're not going to prove neither convergence, but an intuitive way that we can believe with our experience, okay, have a little iterative scheme to get this going, okay? So the way to do this is, let's think that we have this function, f of t. So this leads us to thinking of this. We have this function f of t. Let's see that. It's like this. So we create this function, you see? And if I know the t so that this guy is 0, I have found the right angle to shoot. Right? That's basically what it's saying. So once you put in your mind that, you think, okay, finding a 0 of a function is a little bit, is what? What's the word that comes to our mind? Newton's method. Right? Okay. So, but the thing is that we don't know this function. Right? We don't know what f is. Okay, no big deal. So we're going to end up using Newton's method, because Newton's method you use, say, the derivative, or if it's more dimensional Jacobian, whatever. We don't know the derivative of this guy, so we're basically going to use what's also called for the Newton's method, the secant method. Well, but the secant method, which is the secant for the derivative, is basically doing a finite difference of the derivative of this guy. So we'll see this, okay? So let me write it. So let's, yeah, I can use this here. So basically, I'll go to the other board. Okay, so the secant is basically from the geometrical point of view, right? So basically this means the following. So let's first use Taylor, right? To write this. And then as in Newton's method and approximating after this, we have that. I have this, right? So what have I done here? So as in Newton's method, so I'm putting here basically it's an approximation I have done. And okay, I've hit the 0 and I've truncated, okay? Do I have this right? Yes. And this eventually, well, the notes you have one step, it's very easy, but, and we have that this. I put it like this. This yields the sequence, if I may call it this way, because it's our sequence of TKs. This is wrong, sorry. It's not wrong, but it's not really wrong, but it's more explicit like this. Okay? So basically, right, we've used things like Newton's method. This is sometimes called the secant because this guy approximates the derivative by 2 points. So it's like a secant, right, of the curve. No big deal. It's basically, for us, it's basically just if I was teaching this in a calculus course, this would be the secant. But here, it's basically a finite difference, right? First order finite difference for the derivative. And this is our sequence of points. And therefore, the shooting method, we have like, in the notes I wrote like this, PVI 0, which is our first initial value problem. We can do this. We can call T0. Just, I mean, if we don't have information, we just use the slope if it was a straight line from one point to the other, right? We don't have it. The second PVI 1, we don't have this guy yet, right? So if I put k equal to 0 here, I'm getting T1. I have the T0, but I don't have the Tk minus 1, so I still have to cook up some approximation, and then I go afterwards using this formula, okay? So our second sort of attempt for our PVI is this one, using what happened in the previous case. It's a little bit like a straight line. Using, or let me put it here like this, T, this is how I put in the notes, Tk, k plus 1, then here I start using the sequence. Okay, so this is the shooting method, and then we're not doing any specific analysis and so on, right? There's more to it, as I said, there's like the book. Just to remind you, there's a book. There's more, I believe, but the one I know is a book by Herb Keller, book, specialized on shooting method. It's only on the subject. Of course, it's like a thin book, but with numerical analysis associated to it. Herb Keller was a numerical analyst. Okay, so this is just a little brief thing on boundary value problems for ODEs, but now let's talk about Laplace equation, okay? And I'm going to start talking today on standard things for Laplace equation, basically finite difference method. And then I think next class, not today, I'll talk a little bit to you about boundary integral methods, which is something a little more unusual, I would say, to see in PDE courses, at least first PDE courses. Okay, and then I'll start adding here and there some things more advanced, because we're getting, right, beyond in the second half of the course, you already have material to understand more advanced stuff. Okay, so Laplace's equation, an elliptic equation. So let's see some things about Laplace's equation. I'll remind you about things you probably know, maybe others you either don't know or don't remember, no problem. So let's say we are in this rectangle, okay, and we might want to solve numerically the Dirichlet problem or the Neumann problem. So here, the boundary conditions I'm going to, use for the Dirichlet problem, it's G. The boundary, or the Neumann derivative. Sometimes you put du. I don't know why I put partial differential equation, but du. Also on the boundary, okay, du dn, the normal derivative. Okay, and so our domain is okay. So some of you have seen, right, they have done PDEs and applications with me. Some of you are doing PDEs now here, master's course. Some of you have done it as an undergrad and so on, but maybe as an undergrad don't see everything. This problem here, there's compatibility conditions to be satisfied, and also the solution, is it unique? It's not unique, right? Because we can get u up to a constant, right? Any function that's harmonic plus a constant satisfies this, and plus a constant satisfies this. And in fluids, we see that too. When we study in particular potential flows, where u, we call it phi, right? And phi is the velocity potential. I might give you examples later on in the course. That's why I'm already mentioning it. So grad phi is the velocity of the fluid, and so on and so on. Okay, and we can use complex variables. I'm planning of mentioning this later on in the course. You have a question?
In the PDI 0 is not beta minus alpha?
Sorry, where?
In the formula, PVI, well, there's...
PVY here?
Yes, not beta minus alpha?
Yeah, sure. Sure, sorry. Just a slope, thank you. It's good. Hope the camera gets that and records it for eternity, right? Not leave it my mistake, thank you. Okay, so if we're solving this problem here, right? Say, let's think first the Dirichlet problem. I mean, it's easy to solve this problem with, even if I hadn't told you what to do, with the material we have, right? Because what is the first instinct? Oh, I'm going to solve this problem. The domain actually for finite difference is a nice domain, right? Later on, I'll not remind us, because probably some of this you haven't seen, some of you may have seen, is then how do I solve in a domain like this? It's more complicated, right? Solve numerically in a domain like this. You can still do finite difference, but then the boundary is more complicated and so on, right? So we'll see this. I'll mention about this. Now, if we're solving this domain, then let's just use finite difference, Taylor series, and actually we already saw how to do this. Let me remind us, right? So by Taylor, we have that uxx, the second derivative, right? We go and actually use symmetries and so on. We have the centered difference, I plus 1j to ij plus ij minus 1 delta x squared I have this, and for the other one, okay, here's wrong, see, wait a minute, I minus 1 j, and here it's I, j minus 1. Using eta, yeah. Okay, basically this is just Taylor polynomial to some extent, okay, canceling things. So this is our centered difference for the second derivative. I think we've seen this. I hope I have the indices right. Yeah, I plus 1, I minus 1, j plus 1, j minus 1. And here is our molecule for the method where this centered node is ij. Well, still I have to write the problem, the thing. So our this is called sometimes the 5-point molecule. It's the most standard method, right? It's going to be let me skip one thing, or else I'm going to spend too much time. 5-point molecule with a uniform grid in the sense that delta x is equal to delta y is equal to h. Some cases we can do that, okay? And then it makes our life a little simpler. Probably it's simpler, at least in the class, so I can write down the expression. Okay, and look what happened. Okay, so if I didn't use a uniform grid, sometimes we can't. The domain might be a long rectangle, right? Doesn't mean then you might not need to use, depending on the boundary conditions. Say, oh, it's varying different here than the other direction, so I can use a delta x different than from a delta y. Well, doesn't matter. Then the numerical method is going to be this plus this equal to 0. Let me highlight what I mean by this, right? These two guys here, right? this plus this equals to 0. Now, because this guy is the same, this plus this, right? I can cancel out with 0, and I get this formula here, right? So this expression here. So what is nice about this expression? Do you see? What is the first thing? I already said, I read that, advertised. I like this, and first, right? Why? What is the nice thing that I immediately see, and that sort of connects with PDE theory, not numerics, that connects with PDE theory, which this formula, simple, is already cool, is already good. That is very good. Mean value theorem, right? And then it gives us also the maximum principle out of the mean value theorem. Because look, the value at the center of the molecule is equal to the arithmetic average, almost said in Portuguese, average of the other guys, of these 4 guys, right? And that goes back to PDE theory, where we show mean value theorem, maximum principle, which is important to prove sometimes uniqueness and so on. And so if we think of temperature, for example, which is a stationary heat problem, right? So the heat equation with the stationary solution, the UT goes out, it's Laplace's equation, right? So if the value here in the middle is the arithmetic mean of this guy, right? This guy has to be smaller or equal to these guys, and that's a discrete, will give us a discrete version. This is already the mean value version, right? But it gives us also the maximum principle. So here we have the mean value, right? There's an integral form for Laplace's equation that, right, the value at the center of a ball, or right, be it whatever dimension you are, is the average of the boundary value on the shell of the sphere. Okay, this guy is a discrete version, so we have the mean value. Okay, and also gives us a discrete maximum principle, which is that the maximum is attained where? On the boundary, right? And also we have a minimum principle if you take minus and okay. All right, so that's already a very simple thing. Okay, good. These are the comments in the next page. So let's discuss, let me write this principle here so I can use this space. Okay, now let me do a drawing here so we can discuss a few very simple things. But I think it's good always to discuss and call attention. So I made here a very simple grid. Let me put nodes with colors, as I did in my notes. And let me put, because sometimes the colors in the video don't appear so well, let me put this colors, but also squares. And let's see, the numbers I used was 0, 1, 2, 3, 0, 1, 2, 3. Okay, and then I also call these 1, 2, 3, 4. Okay, so I think I'm okay. Let's see, for the discussion, which is simple, but it's like sometimes you got to make a simple discussion to be complete and to refresh our memories if this is not. So what have I done here? This is, of course, a very simple grid. I would never probably in practice solve something with it, but just so we can discuss things. So if I'm solving a Dirichlet problem, on this grid, right, you already understand my sort of color or whatever convention I am using, right? The nodes I need to find my harmonic function are, I number them 1, 2, 3, 4, right? I only, on the boundary, I only need Dirichlet data at the squares, right? Because say, at the corners here, nobody talks to the corner because of my 5-point molecule, right? These points don't affect, right? This, I mean, in the discrete, the discrete solution. Okay, so this is just one simple thing, right? So, so in my notes, I wrote something like this. And here and there, I will indicate to you, this is so simple. I think, you know, if you, as I told you, some things I'm catching from different books, right? So this I know there's in the Burden and Ferris book. It's also a book for finite difference, and this part I'm going to be using. And if I remember, I mentioned, which is Smith's book. This is on the list of books I left on the boundary. For some things, Smith is very good. It's already sort of an older book, but it's good. Also, these things are classical things. Okay, so let me put here node 1, 1. I'm call this V1, 2, 1 is V2. One, 2 is V3. Okay, and I think my notation I'm saying like this. This would be the solution, and this would be the numerical solution. Okay, so this is the notation I'm using. I think it's from Smith. So what I'm saying here is that since I mentioned that U is the harmonic function, so U at node 1, 1, see 1, 1 is V1, the numerical solution. That's the notation, right? I think Smith used. 2, 1 is 2, 1 is V2, okay? So no big deal. And therefore, I think I better write it here. We have, I'm not going to write it for all of them, but U. Right, I'll just write for these first two ones and then. Etc. Okay, and we get a system in the form AX equals to B, where X for this case is just going to be V1, V2, V3, V4, and A is going to be minus 4, 1, 1, 0. Okay, we have this matrix. Very simple, right? But this is just to show to us one thing, right? In this case here, we barely can see, but like, let me put in colors maybe to highlight. matrix is banded, right? It's banded. It is, for this case, right, it's diagonal dominant. And, right, because these guys here are boundary values, we know them. But one thing to call attention, right, there's several ways to deal with this. I'll mention maybe this later on, but I'll mention this a little bit now, is that, for example, numbering of the nodes is very important. Because, for example, the matrix is not always going to have this. Here it's like pentadiagonal, 5 diagonals, but it's not always going to be like this, right? For example, just imagine if you have a domain which is like this. Okay, and these are your nodes. Depending on how you number this, right, there's usually, sometimes it's called lexicographic if you number them like this as you're writing, right? And there's all sorts of strategies also when has big matrices and so on. I don't know if I'm going to talk about this in the course. We'll see, right, as I choose things as we go along with a little more advanced things on different strategies and so on. But note that, for example, this node here, let me do in colors. Here's our 5-point molecule, right? So this is X, this is Y. And MATLAB has some routines sometimes to deal with if we tell MATLAB that the matrix is sparse or this or that, it takes advantages of the structure of the matrix, right? But we got to sometimes help too. So here, what is, let me make this, just make sure that the video, the nodes I'm talking about become more evident. I don't know if the white and yellow have enough contrast in the video. But what is the best way maybe to number these nodes? Let's say that this is node, let me just guess. It's a 30th node, right? Just put it like this. Or maybe better, I'm not numbering the nodes. Let's first number like this as I was doing the other way. This is like 30, right? It's like 0, 0, 1, 2, just a little bit in that sort of reference number. It's not really the coordinate, but it's like a number, okay? So what is the best way to number these nodes? So if I number it like this, let's see, this is going to be the node 1, 2, 3, pa, boom, pa, boom, 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 and this is going to be 31, 32, boom, 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 60, 61, 62. Okay? Now, if I number like this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So which way is it best to number it? In the sort of lexicographic way, or kind of lexicographic, but in the vertical direction? You see, at first it's no big deal. It's just labeling guys, right? Right? So this is, again, 1, 2, 3, 4, 5, 6, 7, 8. Right? To me, it seems it's better to number it this way, right? Because then the band of the matrix is not going to be so big, right? Because here, if I number like this, it's going to be 1, 2, 3. So it's going to be 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 8. This is 2. So 2 is talking to 8. If I number it like this, it's going to be, this is going to be 2 talking to 31, then talking to 62, whatever. So it just makes the matrix structure different for just numbering reasons, okay? And MATLAB has some cool, I even forget the name, but has some cool routines to reorder matrices and so on. And actually, there's a way you can visualize the matrix. It doesn't, right? It puts a little bit like, just like a different color where the matrix is populated, whatever. It's kind of nice. And there's many routines for that. I even forget the names. But this is just a comment, okay? Now, let's leave it at this for Dirichlet problems, right? I'm going to do a brief introduction for the finite difference because then I want to talk eventually, right? This clock is not working, okay. Eventually on other methods like boundary integral formulation. But let's go then briefly through at least the standard things. So if we're talking about the Neumann problem, so how do I solve the Neumann problem? And now let me put how I'm considering this notation. Well, my notation is bad in the notes because I'm putting this as total derivative. It should be partial derivative. Sorry. I mean, it's going to be obvious to see. Okay, so sorry, okay, in the notes, well, I don't like, I have to someday clean my notes, right? I have like total derivative here. It doesn't make sense. It's partial derivative, right? I have D. And I was like, as I'm writing here, I was like hesitating with the signs I have. Why do I have these signs? But basically, this is like on the unit square. Sorry. So as I was writing, I was thinking, this is, say, from 0 to 1, from 0 to 1. So I'm solving a Neumann problem here on the square, the unit square. Okay? And I was, for a minute, as I'm writing, translating, and talking, and making mistakes sometimes, so I was thinking, why do I have this minus sign here? Well, it's because the normal derivative here is in this direction. And the normal derivative here is in this direction, right? So it's minus delta x, right? Okay. And these are the functions over the faces of the method. Okay, so let me erase this. So let's see, do you have ideas how to solve this problem? Have you seen this before? Just out of curiosity, I always like to learn also from you what is a review, what is new. Sometimes it's not quite new, but some things appear in a slightly more advanced way or whatever. Doesn't matter. Do you know what I'm going to do now? I mean, how do I solve this? Have you seen how to solve the Neumann problem with finite difference in this scenario? Who of you have seen this? Masa has seen it? You too? Okay, so what do we do? I mean, there are many ways to do this with finite difference. So which way would you do it here? Say it. You could say it, Márcio, no problem.
Quando eu fiz, eu calculava os primeiros pontos após a borda, a condição de Neumann, e depois eu usava a morando com os pontos.
Yeah, so I think this is how we're going to do it. So what was said is that you would, if you have nodes, say, let me see how I'm going to do the drawing. I probably have to do the drawing with the same notation because I'm going to use numerical. But basically, you extend the domain, right? So let me rewrite this here. So this one way of doing it, which is like this. It is 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so let me. Oh, so I don't need this one, sorry. So to save us time, let me just number the nodes. It's going to be node 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so this is our domain. Right, and the problem now is that I don't have the boundary values because I have just the derivative. And then, if I understood right what Márcio said, and this is actually a possibility. Is this what you said, Márcio?
You can make this, but you can just approximate the first one inside the domain.
I think this is going to be the second strategy we're going to do. Okay, so if I understand, okay, let me continue. Very good. What I think you said is the second strategy. So this first strategy, and I'll quickly indicate what was said by Márcio, is that this first strategy is like this. We suppose that we have a function that's, has nice properties, is harmonic maybe all the way up to the boundary, say, right? Not always we have that, but we make the domain a little bigger and say, well, this function has nice properties all the way up to the boundary and beyond, to the point where I can basically, for example, at this point here, where I need to impose Neumann condition, I can make a derivative, a normal derivative in this direction. Okay, I'm going to write this down. Okay, so I can say I need to have the du dy direction, right? The dy derivative in this direction here, right? Or actually, the other, sorry, I'm actually saying wrong. The dy derivative is the minus dy derivative. I'm sorry. The minus dy derivative, that's a normal derivative. And so I can approximate this y derivative. I need this point here. What I think was what Márcio was saying, and correct me if I'm wrong, which is our second strategy, say, I don't want to suppose that my function it's an approximation, right? And actually, as this guy becomes small, it's just making it a little smoother and a slightly bigger region. The other one is just making a one-sided approximation for the derivatives. That's what you said, right? At this point, you make a one-sided approximation. Okay, so let's start with this one. Okay, so you're going to see, I'm going to use the notation similar as before, so we can say the Neumann condition. Let's give an example. And let's see how we're going to get sort of information we don't know and how we deal with the information we don't know, okay? So let's start. Neumann condition at node 2, which is exactly the one I pointed out. by chance. I didn't even remember that. Okay, node 2. So that means here I have du dy. The notation of the nodes is 1, 0. So the notation is like this, is 0, 1, 2, 3, 4, 0, no, not 0, this is wrong. This is minus 1, yeah. 0, 1, 2, 3, 4. So this is also minus 1, minus 1. So let's see if I have this right. So this is the Neumann derivative at 1, 0. This is correct. 1, 0. This is node 2. This is going to be minus, because the normal derivative, the h at x1. Now, how am I calling x1? My notation here is not. Oh, this notation x1 is not good. I didn't know, as I was reading my notes. Let me write here. Let's do, okay, so this is going to be approximated. So let me write it, and then we'll double check together, but I think I'm using the notation of. Okay, so I'm going to approximate this by 1 minus 1, which is this guy, minus 1, 0, which is this guy here at the boundary, which I don't know the value of neither of these two guys. Okay? And this is equal to minus h0, which was my boundary value, so this is the guy here, minus h0, and I'm calling it at x1, which would be this first point here inside. This is actually bad notation. And then y1, this is bad. I didn't notice this. Well, let me write it as in the notes, okay? Which is x at point 1. In terms of this notation here. I think that's what we're doing, okay? Not the best notation. I apologize for that. But still, we don't know this guy. I mean, this guy is actually a point outside the grid, and this guy is a guy that we don't know the value. So we don't know these values yet. So let's keep that. But that tells me this. This is useful. This tells me that u1 minus 1, so I have the ghost point, which is a point outside the grid, is equal to v2 minus delta y h0 x1. Okay? So what does this say? The notation is not the best. Again, I apologize. So this just says that because h just depends on x, right? It's saying x at position 1 is here, delta y, and this point here is a point that, okay, it's on my domain, but I don't know its value. So at least I'm rewriting the value of the ghost point in the sense that it's of the extended domain in terms of a point in the true domain plus this guy, okay? Let's leave it at that, and let's try to cook up a system that then we're going to solve for the values of interest. That's basically it, right? The notation is, as I said a few classes ago, I have to at one point make the notation uniform in the way it pleases me and I don't get confused. And you don't get confused, it's more important. So for node 5, just to give an example. For node 5, we can get that using the same strategy that u minus 1 is equal to v5 minus delta x g0 of y1, right? Using the similar strategy. And then using the fact that we are asking for our solution in the discrete sense, right? To be harmonic. Up to the boundary, then we get this. Okay, this is just asking that it be harmonic to the boundary. So we're using the ghost point, right, to apply the 5-point molecule. But we have written over there the ghost point due to the Neumann condition in terms of other things. And this becomes something that will lead us to an okay system to be solved. Okay, and basically, this first strategy I can more or less end here. So you see how the story goes, right? We used the ghost, some ghost point, which is an extended domain, and say, okay, let's, for numerical reasons, let's try to find a harmonic function that's smooth all the way to the boundary, and also have this slightly extended domain, which is actually just a delta y bigger or delta x bigger, just the h bigger. And then this is just a 5-point molecule for using the ghost point and using delta x equal to delta y. Okay? But this guy, I don't know, I have no idea who he is, but using the Neumann condition, we rewrote it in terms of the guys inside. This is what has been used here. We wrote it in terms of v5. And, and then at the end, this is going to give us a system of the type ax equal to b, right? And at the end, we're actually going to get, within this approximation, we're going to get v5. I cannot see. You guys can probably see better than me over there. v5 is on the boundary, and all these guys here are inside, but I think one of these guys is also on the boundary, right? Who else is in the boundary here? Please look at me. Well, I can look at my notes. Right, so it's, it's V5, V6. Oh, V1 is also on the boundary. right? Do I have this right? Yeah, from my notes, yeah. And we actually, anyway, and at the end, when we solve the system, we're going to get the corresponding Dirichlet data associated with our Neumann approximation. Remember, those of you who did PDEs with me and are doing PDEs now or whatever, but now refresh our memories next class when I do Green's theorem, Green's formulation for the boundaries, that the Dirichlet data has a functional relation with the Neumann data. So here I'm imposing some approximation for the Neumann data, and I'm going to get back, quote unquote, the corresponding Dirichlet data to that approximation, which are these boundary values. Okay? Fine. So this, okay, now I have the book again. So this strategy I used, right? This strategy I used was from a book, which is actually a good book, and I like it for certain things. By Ames, I think I have it on the list, but let me write it here because I'm not so sure. It's called Numerical Methods for Partial Differential Equations. Academic Press. It's like from the 70s, maybe. Where's I put the date here? No, 92. No, it's not that. So it's a good book. On the other hand, say Strickwerda suggests, for example, I think what Master said, which is a one-sided difference as a strategy. So he gives us two options. Which is second order. Or this one, which is a first order difference. Okay. And which, of course, I mean, depending on the problem, right? If you can get higher order, use higher order. The central difference is second order. So first, I would go for maybe this one. But anyway, there's discussions in the book. Not a big deal for certain problems. And one thing I should say is that, as a comment, is that, as I mentioned, the Neumann problem does not have a unique solution. Okay? So this might affect the matrix, right? Depending on how things are done, the matrix could be either singular or nearly singular, poorly conditioned. So one thing to do is add another condition, for example, to set the constant that you want. Okay? So for those who did fluids with me or PDEs and we saw potential theory problems, we know that the velocity depends on the constant, right? I mean, if you're solving a problem where you want to get a potential, where the gradient of the potential gives you the velocity field for a fluids problem. So setting the constant just sets where your zero level curve of the potential is going to be, right? So you can say choose a value, say the average of the potential is going to be 0, well, at some point, so you choose a constant, and that sort of helps getting a better system to solve on the computer, okay? So be aware when you're solving a numerical problem. Okay, I have some minutes, maybe not to do everything, but let's use it at least to get started and tell you what we're going to finish. Now, a little bit of numerical analysis, right, for these problems. What we're going to finish next Thursday. So some numerical analysis for the Poisson problem. And here I'm following Smith's book. Okay, so as I prepared this so many years ago, choosing interesting things from here and there, and I see that someday I really have to sit down and organize things better because the notation changes. But at this time of the course, I trust you already, your experience, right? We're not beginning the course and getting things straight. And if we were doing research and reading different papers, for example, notation changes, right? So, but please don't get confused by the notation. So let me summarize, excuse me, what Smith's saying. So he's using this is basically our grid. This domain is our discrete domain grid. And let's think of this, let's do analysis for this simpler case where we have a uniform grid. This is up to the boundary. Okay, that's why the bar. So this is like interior points. So let me write here the notation without writing all the blah, blah, blah. Well, the border is okay. And we have the 5-point molecule in mind. So, and it's Poisson problem. It's a Dirichlet problem. Okay. And here's his notation. The boundary data. Okay, I'm not going to write. Okay, no, I better write just so that we know the notation. Where Lvij, sorry, is equal to 1 over h squared okay, this is the 5-point molecule. Okay, and let's put it this way that all grid functions are smooth, meaning all the grid functions involved, V, F, they have the regularity I need to do what will be done. Okay, let's not get hung up by conditions that would give us trouble. Okay, let's see how far I can go today. Let me at least show you the results, and then maybe we'll do the details next class, right? I'm not going to rush because I'm not going to be able to finish. So the notation is this. U is the exact solution on the grid, right, as a grid function. And right, satisfies basically this. Okay, the other thing we need to know, well, Eij is the error. Okay, of our right? This solves Poisson's equation. This solves the discrete Poisson's equation. Another thing is that this is our local truncation error, ij. Let's see if we agree. So if I apply the discrete operator, what is said here in this question, I apply the discrete operator on the error. Okay, this guy will not give us f because it's the solution of this, right? But it's going to basically give us something like f minus the truncation error of the grid values of f minus the truncation error of the 5-point molecule. So basically, I can write this like this. Okay, and I'm not even, in the notes it's written where this guy and this guy some point in between, right, the node points and so on. So what else? So basically, let me finish say the hypothesis, and then I'm gonna state basically. I think that's the best I can do. I'm gonna state the theorem I'm gonna prove, right? And we'll do this last class, but I'll have to remind you next class. Remind you of these things. Okay, so we can then say that the maximum of this is less or equal to over 6m, where m bounds the fourth derivatives of u, right? So we're saying that u is smooth and so on. We have this domain, okay? This bound domain, and therefore we can say this, right? This is bounded by, let's suppose this. We have this m that bounds this in this way. Let's see what else I'm going to say. Okay, let me just use this space, which is we're going to use the following theorem to actually show that the method, the 5-point method, converges the second order for the Poisson equation if we have this hypothesis, which is the theorem we'll say as the following. I'll come back to this next class. We're going to say that the maximum of V in the interior of the grid can be bounded by the maximum of V on the boundary. But this is for, first we're going to show this for any function with a certain degree of smoothness. We're going to do some estimates. Okay, so basically we're going to show this, that where V is just a grid function, not necessarily, sorry. So take a smooth function, a grid function. This is, even though the notation here is V, does not solve this yet. But what we're going to use the fact that take a smooth Green's function, smooth grids function, tripping on my tongue, smooth grids function, and we can do this bound. The maximum of this grid function inside is going to be bounded by this value plus this is the operator acting. It does not necessarily solve Poisson's equation. And we're going to use this for our needs. And what is going to come in to the proofs and everything that's going to come together is basically things that also you might have seen it in the PDEs course, which is, and comes back to like what we said, the sort of, when we have the mean value theorem, right? We also have a sort of, which is not a mean value theorem, but is a bound when the function is called subharmonic, right? When the function is harmonic, the value inside is equal to the value on the shell, right? When it's subharmonic, it's smaller or equal. If it doesn't, I'm not getting wrong. I think it's smaller than equal. That's subharmonic, and which means its Laplacian is greater or equal to 0 and so on. Then we're going to get a discrete version of that, right? And then use that to show the convergence of the numerical method using. So it's going to be, it's good as an exercise. It's going to be a technical sort of a proof of thing using auxiliary functions. You're going to see this next class. And then we're going to show that actually if V satisfies this, right, with a 5-point molecule, it will converge to order h squared. Okay. So this is what we're going to see next class. So we're going to see some auxiliary things for this theorem. And then at the end, it just follows through. Okay, the proof that actually, if I recall, it is sort of, has a sort of a discrete subharmonic, that is in Smith, but we're not going to use that. Prove it. We're going to use it and then continue. But anyway, details next class. Okay, so plan of next class is to finish this up. Okay, and then I will move on to something which then later on I might say more about finite differences, but I want to move on to showing you things with the boundary integral formulation of Laplace equation and how one can do it numerically. Okay? And here and there, as we go now, move towards the end of October and then into November, also start showing you a little more advanced things, maybe even related to my research or not, so you can see all these things coming together in waves problem, more complicated. We'll see. That's not something I have not even fully organized in my mind, because usually at the end of the course I start putting here and there more advanced stuff, okay? And maybe things also for you to read and make reports. We'll see how it goes. Okay, so let's finish here.